Hi guys, welcome back to Data Every Day. Today we are looking at a dataset of bus engines. So each record is a bus. We have a type of bus, the year, month, and the miles, and whether the engine was replaced or not. We're going to try to predict this column, whether the engine was replaced or not based on the other columns. But we will do some EDA first because this is a pretty simple dataset. So let's go ahead and hop into the notebook. We'll use a logistic regression model. I'm using NumPy and Pandas for working with the data, PyPlot and Seaborn for visualization. For pre-processing, we'll use the train test split function and standard scalar from sklearn. And our model will be logistic regression. And finally, we will use the classification report from sklearn for analyzing the results. Let's go ahead and import all of that and load in the data using pandas.read.csv. We can grab the file path to the CSV file right up here. I'm going to copy that, paste it in, and we can take a look. So it's a very simple data set. We do have a nice number of rows, but we only have 7 columns, and 2 of which are not useful to us. These are both ID columns. This is just a separate index column, and then these are all actually these refer to specific buses. So it looks like maybe multiple records taken from maybe for each month. And whether a replacement was made for that month for a given bus. So the ID is which bus it is, the group is what group the bus was in. Alright, so let's get a little more info at data.info. So looks like there's no missing values in the dataset, and in addition we have all numeric data, so no string or object columns. So we'll start with EDA. Exploratory data analysis. I'm gonna make 3 different plots for visualizing the data. So first thing I'll do is a violin plot. Violin plot is a nice way of seeing the distribution, sort of like a box plot, but you don't get the little outlier dots. Instead, you get a sort of like probability distribution violin. So let's take a look. We'll make a new PyPlot figure. I'll make this 16 by 10, and then create a Seaborn Violin Plot. And on the X, we're going to what we want to do here is show how many replacements were made based on the miles driven and within each group. So we're going to use 3 different arguments here. On the X-axis, we're going to show the group. So we're going to have different groups along the x-axis. For the y, we'll show the miles driven. And the hue here, that's going to be the color of the violins, will be given by whether or not an engine was replaced. And let's just give this a nice color palette. So I'll use the HUSL color palette. And then we will give this a title, miles per group, and we'll show the plot. Alright, so here's a violin plot. So you can see we have different groups, and then the color represents whether examples that of engines that were replaced and examples of engines that were not. So you can see it looks like these 2 groups have no so group 50 and group 870 do not have any replacements made. But within the groups that do have replacements made, which is group 203 and group 530875, you can see that the replacements occur much more around the high mileage than the low mileage. So only when a certain number of miles have been driven, we start to get replacements. Down here, we don't get any replacements, and down here, we don't get any replacements. And you can note there are no replacements from 50 and 870, possibly because we do have pretty low miles driven in both of those groups. Alright, so now I'd like to visualize replacements done over the years. So for this, we're going to use group by. So if we take the data, we want to know how many replacements are made for each year. So let's group by year. And that will create a group by object. If we were to turn this into a list, you could see the data frames in there. Each data frame is a group, which is all the examples in the data frame where the year is equal to 1975. This group is all the examples in the data frame where the year is equal to 1976, and so on. So what we can then do is take the sum over these groups, and oh, not as a list, we have to remove that. And then we can see the sum of every column for a given year. And so here you can see the number of replacements made in a given year. So let's use this as our line chart. We'll do a line graph. So we'll just take the replace column from that, and this is replacements made over the years. So let's do a new figure with a figure size of 16 by 10, and we'll use sns.lineplot, and the data is going to be this thing. That's it. We'll just give it a title, replacements made over time, and we'll show it. Alright, it's a very simple line chart, basically just showing replacements made over time. You can see that actually as time goes on, more replacements are made. So if, I'm not sure if maybe the bus, it doesn't say much, but if the buses were new at this time, it makes sense that as the years went on and they were used more, we get more replacements. Alright, and the last visualization I'm going to do is I want to see replacements by month. So we'll tally them all up again. We'll just grab this. So actually just this. And that looks like this. So if we change this to by month, we can see the total replacements made in each month. So this I'm not going to do as a line chart, I'll do it as a bar plot. So plot.figure with a figure size of 16 by 10. And we'll do seaborn.barplot, where the x-axis is going to be the month only, and the y-axis is going to be this group by. And I want to actually change the text on this, because if we give this a title, replacements by month, and show it, you'll see that we have integers as the labels. So let's go actually change the tick marks. Plot.xticks, and the ticks, which is the spacing, will just be evenly spaced. So we'll make that a numpy a range with 12 values, one for each month, and we'll shift over the markers by 0.5 so that they end up in the middle of each bar. And then the labels are going to be given by the actual names of all the months. So I'll just copy those in to save on time, like that. So we can now see them at the bottom. Oh, actually, we don't have to shift. That's my mistake. There we go. So, yeah, it looks like most of the replacements are made during this spring, really the summer season. Looks like May through September have the most replacements, maybe with the exception of August. So yeah, so that's what we'll do for visualization. Now let's move on to pre-processing. So let's make a function pre-process inputs, and this will be a very simple function since it's a very simple data set. I will just copy over data frame and return the data frame. So this is just going to create a fresh copy of the data that we can use for to make all our changes to. We'll pass in data, call the process version x, and now we can do our changes here. So the first thing I'm going to do is drop the index and ID columns. So df equals df.drop. So unnamed 0 is the first one, and ID is the second. And we'll drop this from axis 1. Alright, and I think that's it. I mean, we really don't have to do anything else. Well, I dropped the ID because... Okay, you know what? Actually, why don't we keep the ID? The ID column actually is not unique for all of them. It's different buses, right? So if we look at the unique values in ID... Whoops. So there's a bunch of different buses, but not anywhere near 8,000. So we'll keep this column on. Well, so this model would only be good at predicting for buses within the current dataset. If we wanted to make it generalized to all buses, regardless of where they come from, we would want to drop ID and group because these two are reliant on a certain setting already. Okay, so now we'll split df into x and y, where y is what we're trying to predict. In this case, it's the replace column, and x is all the rest of the data. So we'll drop replace from axis 1, and those will be our x and y. Then we'll do our train test split. So this will use the train test split function from sklearn. We pass an x and y to that function, specify a train size, we'll make it 70%. So 70% of the training examples will go to the train set, and the other 30% will go to the test set. We'll leave shuffle equals true, and set a random state so the shuffle is always done in the same way. So it'll shuffle the data and then split it. And that will return 4 new sets of the data. Now let's return these 4 sets of the data in our function. Get them back over here, and then we'll take a look at xtrain. So this is only 70% of the data, and ytrain should just be our label column. Why don't we get the value counts? We can see the class distribution. This is quite a class imbalance. There are only 43 replacements in the whole train set. So we might want to try to address that in some manner. So we will now scale the data. So actually, these two columns need to be one-hot encoded. Even though they have numeric values, they're categorical because these are independent from each other. This is not meant to be interpreted as a continuous feature. So let's create a function, one-hot encode, and that will take in a data frame and a column. And I'll start by creating a copy of the data frame so we don't modify the original. Then we'll create some dummies. This will be the dummy columns. So pandas.getDummies for whatever column you pass in, and specify the prefix as the column name. Then we'll add the dummy columns onto the dataset. So df equals pandas.concat df dummies along axis 1, so side by side. And then we'll drop the original column from which we created the dummies. So we drop column from axis 1 and return df. Alright, that's the function. So actually before I do the split, I'll just one-hot encode. Actually, is that good? Maybe we should... No, we'll do it after the split. Yeah, I didn't implement the train feature. So generally, when you do the one-hot encoding, you want to make sure that you're only fitting the encoder to the train set. So what I mean is, you don't want to end up with new columns, new dummy columns. So for example, get dummies. Let's use the ID column. Each ID gets its own column, and a 1 in a given location would refer to the original value of an example. Now let's say you had an ID in the train set that's not in the test set. If you use the same function on both the train and test sets separately, we'll get different number of columns, which will not be good for the model. In fact, we won't be able to use it. In the other case, if we end up with a value in the test set that wasn't in the train set, we'll get, again, different number of columns. So we want some way to sort of regularize the number of columns between the train and test one-hot encodings. So we could do this with another function. We could also do it with the one-hot encoder from sklearn, which takes care of that automatically. But for our purposes, I'm not going to do this just because we only have 104 values, so we can almost guarantee we'll get some of each in both splits. But just keep in mind that if you are going to go about this in the right way, you wouldn't want to. You definitely want to build a one-hot encoding mechanism that works for unseen data, so the test set. Because if you want to build a model that allows for new data to come in, you need a one-hot encoder that knows how to handle those the possibility of missing values, or the possibility of having new values in the test set that weren't in your original train set. But for our purposes, more of an educational purposes, we'll use the one-hot encode function up here. So one-hot encode. So we're going to apply this to 3 columns. So for column in, we list them here. So it's going to be ID, oh sorry, just 2 columns, ID and group. So for columns, for column in ID and group, we'll just call one-hot encode, pass in our data frame and the column. That should be it. And you can see the IDs all get their own columns, the groups all get their own columns, and we can now see 111 columns on our data set. Okay, so let's start training. Really start and finish, because this happens very quickly. We're just doing a logistic regression model. Should train very simply. We'll fit the model to X-train and Y-train. It's done. Now I'll get the results. So first we'll get the accuracy. So let's print out, I'll say test accuracy. I'll display it to 2 decimal places as a percentage, and I'll format it. I'll pass in the value that we get from model.score. The score function returns the accuracy value in the case of a classification model. So we pass in the test set, and we'll multiply this by 100 since it is a percentage. Alright, and we get 99.31%. So this may look good. However, my guess is this is not good. Let's take a look at a classification report. So the classification report can give us a little more information on how we're doing. So we pass in y-test, and then we need a set of predictions. So let's get the predictions as ypred, which will just be model.predict on the test set on xtest. So we'll pass in ypred here and take a look. And as maybe you can see, this is doing very, very badly. Why don't we give these some target names? So we'll say no replacement and replacement. Oh, I put it in the wrong parentheses. Alright, so for the no replacement class, we're doing very, very well. We have a precision of 0.99, a recall of 1.0, and an F1 score of 1.0. But as you can see in the replacement class, where you just have zeros all the way across, and these are actually 0. You can see down here, precision and F score are ill-defined, are being set to 0 in labels with no predicted samples. So we have no predictions being made for the replacement. And the reason for this, it may be due to partially uninformative features, but really what's the problem is the support here. That we have only 17 examples in the test set for replacement, and we have 2,461 for no replacement. So the model is just so much more used to seeing this class than it is to seeing this class. Now, there are ways to deal with this. One such way might be to make synthetic data out of the replacement class, maybe by oversampling the class. One such way of oversampling is just drawing samples that are from, like duplicating the data so that we have more examples. Another way is to interpolate between examples. So there's some algorithms like SMOTE that allow you to oversample in a more intelligent way. But I'm not going to do that today. One thing we can do is class weights. So all we have to do is in our logistic regression, we'll type in class weight, and we specify a dictionary that maps each class to a weight. By default, this is 1.0 for both of them. So this is the default values. What this basically allows us to do is say, in the loss function, penalize one class. If we make this 2, we're saying penalize a misclassification for 1 twice as hard as with 0. In fact, just any time we're dealing with a 1 example, make the loss function twice as much penalty. So let's actually bump this up to like 10. Because we have so few examples in 1, we want the model to get to focus 10 times more on the minority class. We run this, you can see we now have the class weights set. Remember, we have 0.99, 1.0, 1.0, and then zeros all across the bottom. Let's watch this now. And it actually did go up a bit. So now our recall went down by 0.01, but that's okay because our replacement now went up. Now, not by much. This really it didn't have a big effect, but it did give us at least some predictions being made in the category. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.